and I'm going to talk to you about the introduction or the use of some entropy concept in the selection of multivariate models. But before doing that, I would like to spend a few minutes just to introduce to you the main goal of this application, that is the estimation of risk cumulus. So risks can be seen as concentrated for many reasons. The picture you saw here is a concentration due to the fact that many risks are located exactly in the same place. For example, this is for a city, big cities around the world, and you could see different balls that are made up of 3 different colors that show to you the amount that is exposed in terms of value and the hazard and the vulnerability. So you could see places where you have a big amount in terms of value of the elements that are exposed to the risks, and other places where the vulnerability is very high or the hazard is very high. I'm going to talk to you in a few minutes just about the hazard, let alone the value and the vulnerability. Going to the flood risk, the cumulation is mainly due to the size of the event. This event, the 2002 event in Central Europe, was also introduced before, and was really a very strong event that covered a wide portion of Germany and also countries around. And this size of the event should be seen as associated to the location of the different elements that constitute an hypothetical portfolio exposed to the risk. So the main goal of the project is to estimate just the hazard component of the risk for a portfolio that is located everywhere. So there is a wide variety of locations. To do this, we studied multi-site and multi-basin flood scenarios, so we would be able to model flood scenarios in terms of intensity, extension of the floods, and frequency. To do this, so we started from different points in space, for example, gauging stations. To do this, we selected 2 different approaches to estimate the joint probability distribution able to describe those events. And one was the copula function and was selected as a benchmark. So in some way the best that is known and that we could apply, and also a QT distribution that I'm going to describe very quickly to you in a moment, because it's just something that was already presented at this workshop a couple of years ago. And you know well the copula function and the power that is behind the copula function, and this separation of the description of the marginals with respect to the description of the copula itself. So this is a very powerful approach. I don't go into detail here, and also here I'm going very fast. So this is a multivariate distribution that is obtained by multiplying a multivariate T distribution by its cumulative probability function, and is characterized by 4 different parameters: location, scale, shape, and the degrees of freedom. And what is important for what I'm going to show to you in a moment is that if you force the shape to be 0, you obtain a multivariate student T distribution. If you force also the degrees of freedom, in this case to be infinite, what you obtain is a multivariate skew normal distribution. So this is quite important for what I'm going to show to you. But now I would like to introduce the application. I'm going to present to you some results that are obtained for an application to the Tanaro catchment in northwestern Italy, and it's a contribution to the Po River. On this picture you could see by stars 3 different gauging stations I'm taking into account, just to have a minimum multivariate approach in this case. And Alba and Cassine are tributaries to Monte Castello, that is located at the outlet of the basin. You could see here the contributing areas, and from almost, I think, was 10 years of observation, we extracted a number of flood events. That's 76 flood events, and in this case a flood event is defined by 3 different measurements at the same time in the 3 gauging stations. So we applied the copula function to describe this data set. What we obtain is depicted here for bivariate projections at the 3 different stations, and you could see with dots the original data set, and with a plus sign what is the results obtained through simulation performed by using the copula function, and you see the ability of the copula to model this data set. I forgot to say, okay, this is a T copula, so the student T is used as description of the copula itself, and the marginal are described by GV distributions. We select the T copula because it works very well in this case, and also because I'm going to use the SKU-T approach, so there is some relationship between the two. Those are the results for the SKU-T distribution in the same plane as before, and you could see also in this case it was a quite good description of the data itself, even if the SKU-T doesn't seem to produce large amounts of discharge for the Monte Castello case. And we propose to use the informational entropy concept in trying to select or in trying to compare those 2 models. I would like just to remember to you that copula was selected as a benchmark, and would like to see the performance of the SKU-T with respect to the copula function. This is the Kullback-Leibler equation for divergence, and is also known as cross entropy or relative entropy. In some ways a measure of the distance between 2 different distributions, or of the distance of a distribution to a data set. So this includes in the logarithm of the ratio of 2 probabilities, and you could guess that we have problems when QDX is equal to 0, because this goes to infinity, and problem if PDX is going to 0, because the logs obviously tends to minus infinity, and so those give to us a lot of problems. Moreover, because in our case obviously it's not possible to solve this equation in closed forms, and we have to discretize it, like you could see at the bottom of this transparency, and we subdivide our data into a number of bins, and we compare probabilities inside those bins, making up that summation, and what we obtained is something like this one. Okay, you could see here the results in terms of the divergence for different bins on the x-axis, from 1 bin, and obviously comes out to 0, to up to 30 bins. I remember to you that we have 76 data in our data set. There is a way to obtain an optimal number of bins in the histogram that was provided by Scott, 79, and if you apply that equation to our data set, it comes out that the optimal number of bins is 6, and this gives to us a a value of 0.093 for the copula function and 0.047 for the skew-t distribution, and those are the 2 points with the red circle around them. And in some way we could be happy at that point, because the smaller the number, the better is the performance of the distribution. Nevertheless, you could see that there is a big scatter around in this plot, and moreover, if you move a little bit on the right, a little bit on the left, for example, if you select 5 as the optimal number of beings, I don't know if I'm trying to obtain this and put this is really very fast. If you select 5, in this case, the discrepancy between the two is such that the copula function performs better than the skew-t distribution. So for a small change in the number of beings used, you are not able to find out what's really the best distribution you have to consider. This was our final conclusion at that time, and we said that, okay, both seems good, similar in describing the data. But now I would like to move a little bit on, and I propose to you a numerical experiment. So we take our data set and we fit a skew-t to our data set, and we generated 1,000 events using that particular skew-t. And then we follow 2 different roads, on the left A, on the right B. First of all, we fit again a skew-t to the 1,000 data set we had, and we start to force the skew-t, and by deleting the component of the shape, reducing at the multivariate skew-t at a multivariate student t, and moreover we force the degrees of freedom to be infinity, moving in this way to a normal, skew-normal multivariate distribution. So we have 3 different levels in box A, a standard skew-t and the reduction to the other 2. On the right, we perform a different experiment by fitting a new skew-t to the entire data set we have generated, so 1,000 elements, or picking up subsets of the entire data set. So we picked up 1,000 values and we fit a skew-t to that data, and or 100 values and fit another skew-t to that 100 values. In all cases, we came out with a new generation of 10,000 values. And we use the Kullback library divergence to look at those data that in some way we already know what the results should be, okay? And we already know that problems starts with empty beings. So when you have beings in which the probability, the simulated probability is 0. So these are the performances of the 3 models with respect to the percentage of non-valid beings, that means to beings with probability 0. And you see here that the worst case is the skew normal, and better when you use a student's t, and the best is the skew t. With the skew t you have 0 empty beings, up to a point on the left you have many beings, because this is the being width. So large being width on the right means you have few beings, many beings on the left, and also the red cycles that are the skew t starts to present some empty beings if you go on the left. This is reflected into the divergence estimates, and here you could see again in green results for the skew normal, in blue for the student t, and in red for the skew t. So let's say that in this case, as expected, the skew t is better than the student t, because this is asked to SQT to simulate itself, because the generation was strictly SQT, and worse than the skew normal. And this divergence is able to identify the differences between the distributions. Sometimes it happens, like here, that the skew normal, for example, looks better than the student's T or better than the skew T. So there are some beams in which, for a reduced number of 0 points or for some strange things, the divergence are very similar. So also a skew normal could seem a good to provide a good result. Moving to the simulations, the fitting performance with a reduced number of points in the data set, those are very similar results to before. 10,000 points in the data set is the red one, and moving up 1,000 points in the data set or 100 points in the data set. Unvalid beings start to increase when you reduce the size of your data set, and also the results in terms of divergence start to increase. What we suggest to do is to take a form of an average of those results, and to have an estimate of this divergence obtained taking into account many different values of beings used to describe the distribution. If you make reference to this equation, in which we sum up all the results you have seen here, and we divide by the number of beings, of different being sizes we have used, you have in this table the results in terms of an overall discrepancy index, and you see that the numbers describe what we expect just before. So skew T with 10,000, okay, this one, it's the best one, and it's better than the student T, better than the skew normal. And if you use 10,000 elements in fitting your distribution, this is better than using 1,000 elements, and is much more better than using only 100 elements. I remember to you that in our model before, that was trying to describe discharge at Monte Castello, we were at the lower level, because our data set is 76 points, that is very close to 100, it is even less than 100, so we couldn't expect nothing better than 0.02. And if you apply this procedure to the graph, to the plot I have showed to you before, you find out that the copula function is 0.123 and the skew T distribution is 0.116. So results also from this tentative are very similar, one with each other. But what, in my opinion, is important, that the information entropy seems to be able really to describe the distance between those different elements of different probabilities, distributions, or the data set. I have summarized the conclusion here, but since I have described almost all of them during my talk, I stop here. Thank you very much for your attention.
Thank you, Giorgio. Questions? Yeah, there is one question there.
So, how it is compared to the usual criteria like the IEC and PEC?
Okay, I don't.
Especially because it doesn't include the parsimony. We didn't see the number of parameters.
Okay, I try to ask two separate things. Okay, we didn't have time to provide a comparison with other methods, and we will do in the near future. With regards to parsimony, I think that there is a strong difference from if we compare a SQT approach with a copula function. There is a strong difference in the number of parameters because of the fitting of the univariate distribution before. And in the other cases, if I compare SQT against QT, the number of parameters is the same. So we will do a comparison with other methodologies in the near future.
Do you have any idea of the advantages?
Okay, in my opinion, this is very, very simple. So it's straightforward and is a simple application, and so it's quite good.
Any more questions?
Why not?
You said there is a problem when p equals 0.
Yes.
Because you use numerical method.
Well, yes.
I understand that p equals 0 is not a big problem because you have the multiplication with p. But what do you do when q equals 0?
We disregard those components.
Yeah.
Okay, we didn't take into account the components in the sum. Yes. If it is zero, we didn't take into account that component because it goes to infinity.
The same big, you have a lot of p.
We have a lot of. If you start to increase the dimensionality of the problem, yes, we have a lot of blocks which have a zero component. Yes.